Welcome back. In this video, I'm going to cover qualitative equilibria 2. So this is Le Chatelier's principle and how to analyze rate and concentration graphs, basically. So let's get started with defining Le Chatelier's principle. So it gives you an idea of what happens when you disturb a dynamic equilibrium. So when you disturb an equilibrium system, Le Chatelier's principle states that the position of the equilibrium will change to counteract the disturbance, and then a new equilibrium will form. So this means that one reaction is favored, which means that the rate for one reaction will be higher than the other to offset the disturbance until they eventually meet again at equilibrium. When you have an equilibrium disturbance, apart from temperature, KEQ doesn't change. So this ratio will stay constant after every equilibrium's been reached, as long as it's a constant temperature. So the first change we have is the reactant or product change. So this is impacting the concentration of the reactant or products, and obviously it will disturb the system, right? So let's see what happens. So we have this equilibrium here, right? This is dichromate plus water forming an equilibrium with chromate ions and hydrogen ions. So what happens if we increase the dichromate ion concentration? Well, by Le Chatelier's principle, since we've disturbed it by changing the conditions, in this case, which is adding more dichromate ions, the position of the equilibrium will change to counteract the disturbance. So how do you counteract this disturbance? You want to remove dichromate ions, right? And the only way that the system can remove dichromate ions is by consuming them, basically. So it's going to favor the forward reaction, which is the one that consumes dichromate. And eventually, by this method, we're going to be forming chromate and hydrogen ions. So their concentration will increase over time, and the concentration of this will decrease. What happens when we increase the concentration of hydrogen ions, example, by adding a strong acid like HCl. So we're obviously changing it. Again, this is the same thing but opposite. So it's going to try to shift to counteract the change. How does it do this? It wants to consume these extra hydrogen ions, right? So if we consume them, we're favoring the reverse reaction, which consumes chromate and hydrogen ions and forms dichromate and water. So over time, if you increase the concentration of hydrogen ions at a certain time, you'll see there's an increase of dichromate after a while. There's also things we can add that don't directly affect the equilibrium, as in they're not reactants or products, but they still impact the concentration. So a good example of this in this scenario is hydroxide, right? We will recall that hydroxide and hydrogen ions neutralize to form water, right? Now, there's a way to decrease the concentration of H plus ions in this equilibrium system. So what we want to do is we just want to add it like a base, right? So if we add, say, sodium hydroxide, if we add that, we're adding hydroxide ions into the mixture, and this reaction is going to happen, right? It's consuming this hydrogen ion, so this concentration is going to decrease over time, or suddenly it's going to decrease, right? And then what happens? Now we have less concentration of hydrogen ions, and the system wants to restore the balance. So it's going to try to produce more of the hydrogen ions to make up for the ones that we've lost, right? So to do that, we're going to favor the forward reaction, which produces the hydrogen ions. And due to this, we're going to have less dichromate ions, so the concentration of dichromate will decrease. Yeah. And another disturbance, which is a bit strange is if we just add water, right? So if we add water, okay, yes, it's in the reactant side. If we add it, then by the Chatelier's principle, it's going to shift to the forward reaction, right? It's going to shift to the right. But what happens when you add water? Another thing, when you add H2O, if you add large volumes of water, you're increasing the volume of the entire mixture, right? What happens to concentration? Concentration is number of moles over the volume, right? If the volume increases, then concentration decreases. So you're diluting everything inside the mixture. Now what happens when a dilution occurs? The system will shift to favor the side with more aqueous species in order to try to restore the concentration before. So in this case, I'll just add states. So if we add water, if we add a large amount of water, it's going to dilute everything, right? So the system wants to produce the side with more aqueous species. On this side, we have 1 mole of aqueous species, right? Which is just dichromate. On this side, we have 4 moles of aqueous species, which is 2 moles of the chromate and 2 moles of the hydrogen ions. So it's going to favor the forward reaction. If we add a little bit of water, there's no change, basically. The reason of this is because you're not really increasing the concentration. I mean, like, concentration is N over V, right? If you want to calculate concentration of water, it's like, if you do the math, it's something like 55 moles per liter or something. So adding like 3 drops or like 5 mils, it's not going to do anything. It's not going to increase like this number like by much, if not at all, right? So it's not going to do anything to the equilibrium. So when you add water, there's only change when you add a lot of water. Now the next type of change we have is a volume or pressure change. So remember Boyle's law. It says that pressure and volume are inversely proportional. So what this means is an increase in pressure is a decrease in volume, and an increase in volume is a decrease in pressure. So basically what happens is when you change the volume or pressure, the system wants to shift to restore the balance, right? So it wants to shift in the direction to produce more or less gaseous moles, depending on if you increased or decreased the pressure. So if we look at this equilibrium system, it's very helpful, but you have to memorize this. I think nitrogen dioxide's brown and dinitrogen tetroxide is colorless. So in this reaction, we have 2 moles of nitrogen dioxide forming 1 mole of dinitrogen tetroxide. So it's in a gas syringe, which is closed, and it will form a dynamic equilibrium. Now, what happens when we suppress the syringe? So if we increase the pressure, so we're decreasing the volume first, which is increasing the pressure, right? What does this mean? If we increase the pressure, what do you think the system wants to do to relieve it? It wants to decrease the pressure, right? So how do you decrease the pressure? Well, if we think about it, basically, Avogadro's law states equal volumes of gas or equal moles of gas take up same volume at constant conditions, right? So in this case, 1 mole of nitrogen dioxide and 1 mole of dinitrogen tetroxide takes the same amount of volume, basically. So if we want to decrease the pressure, we just want to reduce the amount of particles that are present, right? So how will we do this? Now, if we look at the equilibrium system, we see there's 2 moles of gas here, forming 1 mole of gas here. If we want less particles in the mixture, obviously we want to favor the side with less moles of gas. So we're going to be favoring the forward reaction, right? Over time, the concentration of dinitrogen tetroxide increases because it's being favored. And because that concentration is increasing, you're consuming nitrogen dioxide, which means the concentration of this will decrease over time. And if we look at the photo here, this is right after it's been suppressed. So you notice how the color is a bit darker because there's there's a high concentration of this initially because the volume's been reduced. But then you know how the color fades a bit? That's because the colorless dinitrogen tetroxide is being favored and is being produced. So that's why the color fades a bit. If we had the opposite change, so if we increase pressure, like going from here, say if we went from here and we pull the syringe upwards, suddenly the concentration of dinitrogen tetroxide will decrease, right? So it will look very, very pale brown. But also we have a major pressure change, right? So the pressure would decrease, right? Because we're increasing the volume. With the pressure decrease, we want to increase the pressure. The system wants to increase the pressure again. So what does it want to do? It wants to favor the side with more moles of gas. So in this case, we have 2 moles of gas here again and 1 mole of here, right? Which side has more moles of gas? It's the left side. So you want to shift left, which is favoring the reverse reaction, right? And eventually this system will kind of look like this again. Now, temperature change, I think is the hardest, one of the hardest changes to understand. Well, like when you change the temperature of the system or the ambient temperature, like by the Chatelier's principle, it wants to shift the system. That's what every change causes the shift system to do, right? But how does it do this? It's a bit more complex. So in an equilibrium system, one reaction is exothermic and one is endothermic, right? There's a pair of reactions. So if the forward reaction is exo, then the reverse is endo. Now, what happens? What do we know about exothermic and endothermic reactions? Exothermic reactions release heat, right? So that means the surroundings get hotter, or the temperature increases, right? Endothermic reactions absorb heat, which means the reactions get cooler, or the temperature decreases, right? So in a sense, right, the reaction mixture can kind of moderate its own temperature. What happens now if we change the temperature of the external environment? So say we look at this system. This is another equation you have to memorize, I think. So this is the ion thiocyanate, which is blood red. Cyanate is colorless, and iron, 3+ ions, are just like brownish. So when we increase the temperature, say for this reaction, A plus B, forming C, let's say that's exothermic. If we increase the temperature, what's going to happen? We notice that in this reaction, in this like system, right, there's 2 reactions going on. There's an exothermic and an endothermic reaction. We can favor one of them to try to decrease the temperature of the mixture. So because endothermic reactions absorb the heat, they're going to absorb the excess heat, which is going to reduce the stress on the system. So by the Chatelier's principle is going to favor reverse endothermic reaction, right? And this means it's going to shift left. Now if we had a decrease in temperature by the Chatelier's principle, we want to increase the temperature again, so we're going to favor the exothermic reaction. Which is a shift to the right. So in this system, right, these are all equilibrium systems of the same thing, but they just have different concentrations of the products and reactants because of the temperature. So this one's cold water, that one's hot water, and that one's warm water. So you can kind of see, right? In the cold water, it's more brownish, right? And in the hot water, it's more like blood red. I know it's a bit of a hard color change to notice, but if you can notice the subtle change, I mean, that's good enough. So what does this mean? In the cold water, remember we said that when we decrease the temperature of the system, it wants to favor the exothermic reaction. So that must mean that this reaction is exothermic, right? Because we know that the brown color comes from these ions. And since this is in cold water, we can deduce that the formation of these ions must increase the temperature. Now we can say the exact opposite for the hot water. So the hot water, there's more thiocyanate ions. So those are blood red. And what does this mean? In a hot environment, the system wants to favor the endothermic reaction, right? But if there's more thiocyanate, that means that the reaction that produces it is endothermic. So that means the forward reaction is endothermic and the reverse reaction is exothermic. So if you get a question that gives you like this, like a picture or something, and asks you to analyze, to deduce which reaction's endothermic or which one's exothermic, you just have to use this reasoning. If you add a catalyst, it doesn't change anything except the forward and reverse reaction rates. It changes them equally, but you won't see any change in like the shifting of the equilibrium. Also, one last thing to note for temperature change, equilibrium is reached at a different temperature than before, right? It can't fully offset the change. So it's going to be either a higher temperature or a lower temperature than before, which by this, like, look, we can tell that these are at equilibrium already, right? But each of them looks different, which is because of the different concentration ratios, right? So KEQ is going to change if you have a temperature change, but that's the only time it will change. For concentration graphs, basically you see here, this is the reaction that's going on. What's happening here? You see there's a sudden increase in concentration for one species. That means that the concentration of one species was increased. I know it sounds obvious, but this means that in reality it's just been added to the mixture. If we don't see any other concentration changes, that means that nothing else was added or nothing else was changed, and only this has been added to the mixture. So in this case, we added more nitrogen. Now we see a gradual decrease of nitrogen as the system tries to consume it. And we also see a decrease of hydrogen because it's on the reactant side as well, right? Now we see a gradual increase of ammonia because it's being produced and favored in order to counteract this change here. At this point, equilibrium reached again. However, there's another disturbance here at this point, right? So if we see a sudden spike in all concentrations, whether it be up or down, we can definitely tell for sure that's a pressure change, or a volume change, right? If we look back at C equals N over V, if we change the volume, we're affecting the concentration of everything, right? Regardless of what it is. And if we like decrease the volume, we're going to increase the concentration. But if we increase the volume, we're decreasing the concentration, right? However, in this case, you see the concentration of all of them increase. So what does this mean? If the concentration is increasing for everything, that means N stays constant, right? So that means V is decreasing. So that means there's a pressure increase or a volume decrease. Going back to what we said about a pressure increase, it wants to favor the side that produces less moles of gas, right? To relieve the stress. What is this? Looking at this reaction, what does this mean? So, looking here, right? We want to produce more gas. So yeah, you see how the nitrogen, it's like being reduced, right? Because it's being consumed. And also the hydrogen's also being consumed here. So you should see an increase in ammonia. I think the graph is wrong. Like, why, dude? You can't even use graphs with the internet anymore. Like, you just like, this is full like gaslighting and shit, bro. Like, what is this even? It's not even right. Okay, so basically, like, if we have a pressure change, like this is a pressure increase, right? No, pressure decrease. No, pressure increase, right? Volume decrease. So what this means is it wants to favor the side with less moles of gas produced. So it's going to favor this side, right? And so there's going to be a decrease in concentration of these and an increase in this. So that means these should go down. Oh no, it is right. Sorry. Just follow the lines. Sorry, this is another thing to be careful of. You want to follow the lines. So why I made a mistake, because see, like, the lines overlap. But yeah, you just need to follow it, I guess. Sorry, my bad. So you can see if you follow the ammonia line, it increases. If you follow the hydrogen line, it decreases because it's being consumed. And here, it's reached equilibrium again here, right? And we have one last change, which is the temperature change. At this point in time, you see nothing except a gradual change in all of the species. Now, what this means is basically like one reaction is being favored over the other. So in this case, they don't tell us if it's an increase or decrease, and we don't know. Given no data, we don't know. So all we can tell basically is that the temperature change causes the concentration of nitrogen to increase and also the concentration of hydrogen to increase, right? It causes the concentration of ammonia to decrease. So that's basically all you can analyze for a concentration graph. There's like a little cheat sheet here. Feel free to take screenshot if you need. But yeah. Now, for rate graphs, it's a lot easier. You need to recall that at dynamic equilibrium, the definition is that the forward and reverse rates are equal, right? So when you disturb it, the equilibrium one rate will increase more than the other until equilibrium is established again. Now here, say this is an arbitrary equilibrium system. There's H2 added, which let's say is like one of the reactions or something, right? Forward reaction, no, H2 is one of the products, sorry. So the forward reaction would increase. The rate will increase because there's more H2, right? So there's more collisions. Over time, it will thin out. And the reverse rate will also like increase because there's more collisions, because there's more particles in total. So it's going to thin out until equilibrium is reached, and the rate will be higher because there's like more particles. Well, it depends what change you get, but usually the rate will be higher, because if you have temperature change or concentration change or volume pressure change, if you increase the volume, you're going to get a decrease in rate because the particles are more spread out, sorry. And if you increase the concentration, you're going to get an increase in rate because there's more concentration, right? That's collision theory. If we increase temperature, there's going to be a higher rate because the average kinetic energy. So if we decrease temperature, there's going to be less rate. If we decrease concentration, there's going to be less rate. And if we decrease volume, there's going to be more rate because there's more collisions. So that's basically it. If we increase the catalysts, if we add a catalyst, sorry, they increase the rate of reaction equally. So what this means is basically like, you see here how the rate of forward and reverse are equal. They're at equilibrium here. At equilibrium from here to here. Catalyst is added here. It doesn't change the system position at all. In fact, it just increases all the rates equally and ends up higher than before. So yeah, that's it for this video. I think next video I'll cover quantitative, so I'll do like calculations and stuff. So yeah.